Hello student, very good morning to all of you. Do you remember what were we discussing yesterday? I think we were discussing about the syllabus of 4th semester. How many chapters are there? How many lectures are required to complete that syllabus? What are the reference book to use? How to study? So this kind of the discussion we have discussed yesterday. What we are going to discuss today, let us see over here chapter number 1, and as we know that there are the 9 chapters, so we are going to start from the chapter number 1 sequentially, that is a Carbanion and their reaction. The name of that chapter, Carbanions and their reaction. First of all, let us see the definition of Carbanions. What does it mean? Carbanion means what? Organic species carrying, or the carbon carries negative charge, is known as Carbanions. Remember the definition of Carbanion means what? The negative charge carries carbon atom are known as Carbanions, means an organic species in which the carbon atom carries a negative charge is called Carbanions. The carbon with negative charge is sp3 hybridized and has tetrahedral geometry, and as we know that tetrahedral geometry of having the tetrahedral bond angle is found to be 109.5 degree, and this type of the study we already hybridization or type of the hybridization using S and P orbital, the possible hybridization, their geometry, the bond length and bond angles, that we already learned. But here particularly when the an organic reaction or the chemical species, an organic chemical species in which the carbon atom carries a negative charge is called as a Carbanion, and the carbon with negative charge is sp3 hybridized and it has a tetrahedral geometry and bond angle found in that is a 109.5. Let us look at the example, suitable example where you will find as a Carbanion formation. Now let us see over here, and as we know that the Grignard reagent, have you heard about? You are already familiar with that Grignard reagent, how it is formed. Grignard reagent is nothing general formula for Grignard reagent or a complex form is it is a organometallic compound, or MgX is known as a Grignard reagent. How it is prepared? Do you remember that? The starting material is a pure alkyl halide treated with pure magnesium metal in presence of dry ether. The resulting compound obtained is known as Grignard reagent, which is a organometallic compound. It is a versatile reagent. Variety of the organic compound we can prepare when that Carbanion is formed, and it is very important. And Carbanion can act like as a nucleophile as well as basis, and as we know that nucleophile and the basis, even though both has a tendency, both carrying as a negative charge as well as the heteroatom containing as a lone pair on it, both are acting as a nucleophile as well as base. But there is a major difference, and that major difference we already learned in our previous semester, in the 3rd semester while studying, I think, Carbanion, studying I think nucleophilic substitution reaction, where we have seen the difference between the nucleophile and the bases. Major differences, I think generally there are two major differences which can distinguish the nucleophile and the carbanion from each other. Carbanion carrying as a negative charge, and when they attack on the carbon atom, they produce there is a formation of the new covalent bond. The bond between carbon new bond is formed, that is and at that time we can call it as it is act as a nucleophile, OH minus suppose. Let us consider OH minus is a nucleophile, and first of all, nucleophile means what? It is an electron rich species capable of donating as a lone pair to the other atom, specifically in this particular case to the carbon atom, and form as a covalent bond. That type of the species is known as a nucleophile. And when it is got as a base, suppose as OH minus is considered as a base when it is attacking, it donating lone pair to the H plus, and resulting compound formation of the compound is a neutral, which is a water molecule, and that time OH minus in this case act as a base. So this is a first major difference between nucleophile and the base. Base can attack or it can abstract the hydrogen atom, or it approaches to the hydrogen atom, whereas nucleophile approaches to the carbon atom and form as a covalent bond. So this is one of the major major difference between as a nucleophile and the electrophile. And second one, that nucleophile is controlled by kinetic factor. Remember, nucleophile is controlled by the kinetic factor, whereas base is controlled by the thermodynamic factor. That is the second major difference between as a electrophile and the bases. Base, because nucleophile kinetic control means what? We can easily determine its rate of reaction, and generally rate of reaction is found in a slow reaction. So we can determine the reaction, how much time is required for the formation of that new bond, whereas in case of that base, there is thermodynamic, it depend upon the thermodynamic, it is related to as a heat, so that get affected. So that is the second major difference between nucleophile and the base. And third one, that steric factor affected by the nucleophile, whereas base does not get affected by the steric factor. So this is the third major difference between as a nucleophile and the bases are there. So similarly here, for example, in case of I am specifically writing here the Grignard's reagent. Directly I am writing over here. Here is a carbon atom, means this is a methyl group I am writing over here, and when it is attached to the methyl in presence of this is known as a Grignard's reagent. This is known as a Grignard's reagent. Methyl magnesium bromide is nothing but as a Grignard's reagent. It is a versatile synthon, variety of the organic compound. If this Grignard's reagent, if you treat with the formaldehyde, resulting compound obtained, followed by hydrolysis, the compound obtained will be the ethyl alcohol, which is a primary alcohol. If it is treated with acetaldehyde, propanaldehyde, or whatever aldehydes are there, the resulting compound is obtained will be the secondary alcohol. Only formaldehyde and the epoxide gives or produce the primary alcohol, and rest of the aldehyde produce the secondary alcohol from the Grignard's reagent. Starting from the Grignard's reagent, we can easily prepare primary alcohol as well as secondary alcohol. And suppose that Grignard's reagent, if you treat with the ketone, you can prepare aliphatic ketone as well as aromatic aromatic alcohol as well as tertiary alcohol. Remember here you are going to you are going to synthesize the tertiary alcohol. So in this way, by using as a Grignard's reagent, you can prepare primary alcohol, secondary alcohol, as well as tertiary alcohol. So depending your need, you can prepare the primary alcohol, secondary alcohol, or the tertiary alcohol. So that's the thing. Now here I am specifically taking or considering here is a Grignard's reagent. As we know that when any metals are inserted, why? Let me tell you one story regarding that Grignard's reagent, how he awarded by the Nobel Prize. Suppose as a Grignard, as we know that alkyl halide RX, right, and where that is a polar compound, and polarity, if you see the nature of that R over there, R is a plus delta charge, means it gets the partial positive charge, and X, as we know that halide groups are they are having a tendency to attract the electron toward themselves or toward itself and get the negative charge. And when these alkyl halide, pure alkyl halide, treated with the pure magnesium metal, and generally the solvent used is as a dry ether. Why dry ether is employed here or used here in this particular reaction? The reason behind it, if there is a drop of water present over there, it catches the fire. To avoid this bumping or that accident, and therefore there is always used as a dry ether for carrying out such type of the reaction. The resulting complex form, which is known as a organometallic compound, and organometallic compound are very important as far as the synthetic utility is concerned, or the utility of the synthetic route you can, because by when it form as organometallic compound, remember here that R group, here what is happening, let us look at here R and then X. As we know that here R plus delta charge minus delta charge, then here magnesium metal, which is a pure, then dry ether is used over there, and resulting compound form RMgX, which is a Grignard's reagent. This one is known as a Grignard's reagent. The starting compound, this one is alkyl halide, right? This is alkyl halide, and this is a pure magnesium metal and dry ether. Just now I already told you that why dry ether is used here, to avoid the accident. If there is a moisture or aqueous ether is used, it catches the fire, there will be there is no formation of the Grignard's reagent. And that's why here always while synthesizing the Grignard's reagent, this is the organometallic compound, and here what is happening, why he did this one? If you look at the nature of R on alkyl group, as we know that they are readily formed or readily available. When magnesium metal is inserted, this complex is formed, the nature of that R is exactly opposite. Now here becomes as a minus charge over there, and as we know that metal always carries the positive charge, exactly opposite. And as we know that more than 75% organic compound containing as a carbonyl group as a functional group, and as I already told you that functional group means what? The atom or group of atom that determine the physical properties as well as chemical property of the particular family of the organic compound is known as a functional group. Or generally whenever we are adding as a reagent, part of the organic compound undergoes as a change, so that is called as a functional group, or in short we can call it as a site of reaction. So that are the definition of the functional group. Means what are the carbonyl group? Suppose as a aldehyde containing carbonyl group, ketone containing carbonyl group, acid containing carbonyl group, ester containing carbonyl group, amide containing carbonyl group, then lactone containing carbonyl group. So that type of the compound containing as a carbonyl group, and therefore whenever you are doing the reaction with that carbonyl group, and nucleophilic substitution reaction takes place, and we are getting as a different type of because when the Carbanion is a form, Carbanion, it can act as a nucleophile, and nucleophile, as we know that nucleophile attacking on the another carbon atom, there is a departure of some living group, or there is a mainly formation of the new carbon-carbon bond, means the new organic compound is formed. Once a new organic compound, new structure, new different type of the physical property or chemical property we can study, and therefore it is and that's why he awarded by the Nobel Prize just by he changed the nature of that R group. So here is a positive, here becomes as a negative, and that's there. And now let's move on to our why when this Carbanion, suppose it is broken like this, because this bond get broken over here, and when this breaks like this, we are going to get here this type of the species. When this bond break, this bond is break heterolytically generally. Heterolytically means what? For bonding for the formation of the bond, it requires a two bonds. And when there are two type of the fissions are occur, one is called as a heterolytical fission, another one is called as a homolytical fission. Homolytically means the sharing of electron, that bonding electron are gaining by each atom, but in this heterolytically, and the sharing of both the electron is acquire only one of them, and therefore here the carbon generally more electronegative in nature, and that's why it carrying as a negative charge. And just now we have said, according to as a definition, Carbanion means the carbon atom carries as a negative charge, that is called as a Carbanion. This Carbanion is formed over there, and rest of the thing don't think about that one. And whereas this Mg and Br, it is a positive charge over there, don't think about this one, only we have got this is called as a Carbanion, right? And when this Carbanion it act as a nucleophile, or a nucleophile can attack on the other compound. And now if you look at as a hybridization of that, it takes as a what we can call it hybridization of this. So if you show the geometry of this, and as similar to as a Carbanion, as we know that methane molecule, in a methane molecule CH4, right? Methane molecule, it shows as a tetrahedral geometry. Here carbon atom is a central metal atom, and then hydrogen atom are present in tetrahedrally, in a regular tetrahedral bonds are there like this. So this is we know that this is called as a tetrahedral geometry, and the bond angle is found to be 109.5. that is a standard bond angle found in the tetrahedral geometry. But here also these three hydrogen atoms are arranged like this. Here three hydrogen atom and this lone pair, that negative charge is nothing but as a lone pair we can call over here. It is here, and more repulsion over there, and these three hydrogen are acquire, or they are present at symmetrically in a tetrahedral manner, and we are going to get over here this type of the compound. This is a tetrahedral geometry, tetrahedral geometry over there, geometry, and the bond angle is found to be 109.5 degree. So that is a bond angle found in this case. So that is a Carbanion form. Or another way, this is the first way. Second one, just like as those are the carbonyl group. Now let us look at here CH2. Specifically for the sake of convenience, I am writing one of the hydrogen atom over here. Here H. Now when base is used here, base can abstract the proton and form as a Carbanion over there, like this CH2 minus charge over there, C double bond O. Then hydrogen atom, this is called as a Carbanion, right? Carbanion. But in this case, what is happening? This carbonyl group is a more electron withdrawing group, and when it is a electron withdrawing group, and therefore this type of the resonating structure, this Carbanion is well stabilized due to the electron withdrawing group, and you are going to get CH2 double bond CO minus and H. When the negative charge generally present on the more electronegative atom, that species is more stable, and this is called as a enolate. This species is called as a enolate. Remember, epoxide, we know that similarly this species is a negative. When the negative charge on the more electronegative atom, that type of the species is called as a enolate. Enolate is a more stable or more reactive than the carbanion in this particular case, you remember. Because why? Because the oxygen atom carrying as a negative charge. Nearly all organic compound that contain CH bond, that contain as a CH bond, are acidic in nature. Acidic in nature because can function as an acid, donating a proton to a suitable base, giving carbanion. Suppose let us look at here. Suppose we have this type of the species, then R, or we can call it as yes. Then carbon atom here R, then CH, and here also as R. This CH, just now I told you that suppose as there is a CH bonds are present, now by using as a suitable base, what is the function of base over here? Base will abstract the acidic proton here. Here is a hydrogen atom, it can abstract proton from here, leaving the bonding pair over there, and you are going to get R. Then here you can put R, then R and minus charge. Now depending, this is the carbon atom carrying as a negative charge, and therefore it is known as a carbanion. So and that carbanion has a tetrahedral geometry, and in this way we have seen as a general introduction regarding as a this carbanion. Now moving toward as the next point, that is a Carbanion formation. How the Carbanion formation, what are the method for the formation of the Carbanion, that we are going to learn over here. There are the different method for the formation of the Carbanion. One method which is known as first one, that is a let us see as a Carbanion formation over here. Carbanion formation. What are the methods? By using that method we can see the general method for the formation of the Carbanion formation. First one, by removal of an atom or group X from the carbon atom. First method is by removal of an atom X from carbon. So this is the first method for the generation of the Carbanion. So it is the most general method of forming Carbanion by removal of an atom or a group X from carbon, and during this process X is leaving its bonding electron pair behind, forming Carbanion. Let us see over here the example R, then here is again R, and here is a X, right? And now when this X group get removed by using a suppose any reagent over there, this can get formed with this, and now leaving that bonding pair behind, you are going to get R, then here R minus charge and plus X and Y, that is a side product form over there, or we can call it as a formation of the conjugate acid. And whatever this Carbanion, this is a form of the Carbanion, and that Carbanion, whether it is a stabilized or destabilized, what are the factors which stabilize the Carbanion, that we will see later on. But here just remember how the Carbanions are formed. And now suppose for example this R I am taken as here as a general reaction. If I am taking here as a 3-phenyl group over here, so what could be the means triphenyl methane chloride I am taking here as an example. Let us here observe this reaction carefully, that the name of this compound is a triphenyl. This is a methane chloride. This is the name of this compound. When this compound, if treated with sodium metal, twice sodium metal, and there is a elimination of sodium chloride, what you are going to get? There you are going to get this type of the formation of the compound Na plus over there, minus charge over there, and 3-phenyl group, and that 3-phenyl, this Carbanion is formed over there, and this Carbanion is well stabilized due to the resonance, because this negative charge goes here, formation of negative charge like this. Here you are going to get this compound get stabilized over there, this double bond. Then you can write here negative charge, this double bond, and this another one I am writing for sake of convenience, this group over there. So in this way, as we know that the number of resonating structure goes on increasing, the stability of that compound goes on increasing. So that is the thing we are going to go to over here. And this compound, when treated with, or instead of writing as this, we can write pH, then pH, then PHCl. This will be treated with NaNH2. NaNH2 is known as a sodium amide, and the same thing what is going to happen here, pH, then pH, then Na plus, Cl minus, and another NH3. Ammonia get evolved during this process, and whatever things are generated over there, that get formed. So this is a second method for the preparation of that carbanion, that is triphenyl methane. Now is a second method from alkenes and alkynes. Second method will be from alkenes and alkynes. This is a second method. From that we can prepare, or we can get, or we can derive the Carbanion formation. Let us see over here second one, from alkenes and alkynes. Alkenes and alkynes, as we already know that alkenes and alkynes, for example, let us consider here CH3, CH3, then CH2 double bond CH2, then here H, C triple bond CH. Remember here there are the three different structures are written. If you observe these three structure carefully, what do you see over here? Here is a carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bonds are there. And as we know, if you consider their pK values, if those pK value are the low, that compound are more acidic in nature, and this type of the pK concept we already learned in our previous semester, I think in third semester, in a chapter number 4, acidity and basicity. There you remember, here the pK values are found to be, here is a 50, I think a 53, 52, then 33, and here the pK value is found to be is a 25 over there, 25. So these are the, I think, pK values of those. And if you calculate as a percentage of S character, and as we know that percentage of S character, how to find out that S character, as we know that there are sp3 hybridization, sp2 hybridization, and sp hybridization, right? And yes, the percentage of here, remember the involvement for the hybridization, participation are 4 orbital are participating, combining together we are getting here the 100 divided by 4 you will get as 25%, means S character, how much percentage of S character present here, 25. Here are the 3 orbital, 1s and 2p orbital. So 100 divided by 3, you will get 3.33 like this. Sp means what? 100 divided, only 2 orbitals are participating here in this particular case. 1s orbital, another p orbital, total are 2, divided by 2, you will get as a 20, only as a 50% over there. As the percentage of S character goes on increasing, the acidity goes on increasing, and therefore it is the lowest. This one is a more acidic in nature as compared to this one, and therefore if this type of the compound treated with sodium amide in presence of the liquid ammonia NH3, what you are going to get? Here you are going to C triple bond, here minus charge, and Na plus, this type of the acetanolide, and this is nothing but as a carbanion, and carbanion can attack on the carbon, and there is a formation of covalent bond, means new carbon-carbon bond is formed, and we are getting as a new compound, synthetic organometallic compounds. So this is the second method for the to get the Carbanion formation. Now let us move on to the next one, that is the third method, and third method for the generation of the Carbanion is the introduction of carbon withdrawing substituent. Introduction of electron withdrawing group, introduction of electron withdrawing group, withdrawing substituent. So that is the third method, introduction of electron withdrawing substituent. By introducing as an electron withdrawing substituent, we can make the Carbanion there. For example, suppose we have this one, fluorine, then carbon atom, fluorine, then again fluorine, here is a hydrogen atom. These hydrogen atoms are highly acidic in nature as compared to the previous one we have, because here is a fluorine atom. As we know that electronegativity goes on increasing across the period. So at a halogen family member, first member is a halogen, and rest of that fluorine, chlorine, bromine and iodine. As we go from top to bottom, the electronegativity goes on increasing, and therefore fluorine is found to be highest electronegative element in the long form of the periodic table, and therefore this one is a highly acidic in nature. So base can abstract that proton, and you are going to get here C, F and F, this negative charge. That carbanion is well stabilized due to the resonance effect. Or instead of that, you can take as a F3C, then C here, CF3, again CF3, and here hydrogen atom, and this hydrogen atom again more acidic in nature than the rest of the thing. So in this way, there are the three methods we have seen, and the last one, fourth one, is a Carbanion from carbonyl compound. Fourth one, the Carbanion from the carbonyl compound. So fourth one, let us see over here. Fourth one, that is a Carbanion from carbonyl compound. Carbanion from carbonyl compound. Carbanion from carbonyl compounds. And Carbanion from carbonyl compound, just now we have seen acetaldehyde, one of the example over there, C double bond OH, and by using as a base, what is going to happen? This will abstract that acidic proton and form as a carbanion, C double bond OH, form as a carbanion. This is known as a carbanion, and that carbanion are well stabilized due to the resonance. You are going to get CH2 double bond C O minus H over there, and this species is known as a enolate. And as we know that this enolate are more stable than this one. I think with this we have seen there are the four methods to generate the Carbanion. Tomorrow we will see what are the factors. Again there are the four factors which will stabilize the Carbanion, that we will see in the next lecture. I think with this let us stop today here. Thank you. Have a nice day.